Hi. Thank you for the introduction, and thank you everybody for being here. So today I'm gonna talk about the applicability of fairness notions. So as you said, this is a joint work with Semi Hiwa from Higher Colleges of Technology UAE and Katouchia Palamidesi from INRIA École Polytechnique France. So I start with the crucial question. So what does it mean for an algorithm to be fair? So for example, should algorithms be fair if they always make similar decisions for similar individuals? Or should we instead call algorithms that make similar or beneficial decisions for all genders consistently fair? Or should we use any other third criterion? So this is actually fundamental because many of these criteria cannot be satisfied at the same time. Now, the main problem here is that fairness is by nature a subjective concept, and there is no clear agreement over a universal definition of fairness. But it can be informally defined as the absence of any prejudice or favoritism towards an individual or a group of people based on their intrinsic or acquired traits. Now, over the last few years, there have been many various fairness notions, and all of them have been formally defined. But one of the issues we noticed in the literature, including the surveys, is that the problem of applicability has not been sufficiently addressed. Here, by applicability, I mean when it is recommended to use a notion, when it is necessary to apply a certain notion, and when it is not acceptable to use a fairness notion. Now, as the work is about the applicability of fairness notion, we started by analyzing a list of real-world applications where fairness is critical, okay? So in each one of these applications, the failure to address fairness might lead to unfair decisions against individuals or subpopulations, like, for example, rejecting a good job application or depriving deserving people of a loan or making misleading judgments or any other unfair life-changing decision. Now, these applications are used to give concrete examples of situations where some fairness notions are more suitable than others. The second step was to identify a list of criteria that can be used as a roadmap to systemize the procedure for selecting the most suitable fairness notion for a specific ML system. So let me say here that in some cases, these criteria can not only indicate if a fairness notion is suitable to use, but whether it is acceptable to use at the first place. Now, these two elements are fitted to provide the most suitable fairness notion in every specific setup using a decision diagram. Okay, so basically this diagram can be used by practitioners, decision makers to navigate the relatively large catalog of fairness notions. So here the rectangle indicates that a fairness notion is recommended to use. The triangle here represents that a fairness notion is not suitable to use, and the circle indicates that a fairness notion must not be used. Okay? Now, here is a real-life example that shows how applying a wrong fairness notion can make an unfair scenario appears as fair. That is, the prediction produced by the system tells us it's fair, and then the fairness notions fails to identify this discrimination. Okay, so the Allegheny family screening tool, known as the FST, is an automated system that tries to predict a risk score about child maltreatment, okay, in the future. So basically, the system takes as input data about children, data about caregivers, and other contextual data, and produces a risk score of maltreatment that can justify an early intervention, in particular withdrawing a child from his family and placing him in a foster house. Now the system was found to be unfair as it uses the rate of referral calls in its prediction, okay? So by referral calls here, I mean calls made by neighbors to report a child abuse or maltreatment, okay? The problem here is that the calls made by the community to report child maltreatment were like more to report non-white families problems than white families, okay? So it's clear here that the rate of referral calls acts as a proxy to the race, the sensitive attribute, which is of course unacceptable, okay? So because it will lead to harmful decisions for people belonging to the minority groups, okay? So as a result, these discriminated families will be like the subject of more scrutiny and more requirements to satisfy, and eventually they will like fade short of these requirements, okay? Now, under these conditions, some of the fairness notions, there is a risk, let me say, in applying some fairness notions. So for example, here equal opportunity, as you can see in its formula, the prediction is based on the true outcome Y. So, and we just saw in this case that Y is not reliable, okay, because it is biased and it is highly correlated with the sensitive attribute through the proxy, the rate of referral calls, okay? So the prediction basically will lead to discrimination against these people belonging to the minority or disadvantaged groups. One example of a fairness notion that can be used and that is suitable to use is statistical parity. As you know, this is, or the prediction of this type of fairness notion is independent of the true outcome or any other feature actually in the data set, except of course the sensitive attributes, okay? Another appropriate fairness notion also to apply is no proxy discrimination, which is actually an individual fairness notion, and more specifically, it's a causality-based fairness notion. So this notion states that the prediction requires a full independence between the prediction and any potential proxy in the data, okay, as shown here in the formula. Good. Now, let's start by the first two criteria, which are very important and should be considered at an early stage of any decision process. So intersectionality and masking. So here, as you can see in the diagram, all the fairness notions that lie in the upper part of the diagram are group fairness notions, and the ones in the lower part are individual notions. So here, intersectionality is basically the type of bias due to combination of sensitive factors, okay, not a single one. Let's take an example here. So assume we have a setting with two binary sensitive attributes, gender and race. Let's say, so men, women, and let's say white, black. So a classifier might indicate that might show a fairness, let me say, of acceptance rates between any or a sensitive factor alone. Okay, so we take men versus women, and then white versus black, so we get fair results. But when we consider any conjunction of these factors together, so here the classifier might identify some discrimination. Okay, for example, here white women versus black women. And in fact, as was stated by Crenshaw in her well-known paper, Mapping the Margins, Intersectionality, Identity, Politics, and Violence Against Women of Color, that black women are particularly prone to this type of discrimination. Now, masking is the type or the form of intentional discrimination that allows decision makers with prejudicial views to mask their intentions. Okay, again, let's take an example. So assume we have a fairness notion that requires equal number of applicants from two different ethnic groups to get admitted to a college. Okay. So what an example of ML system or a biased ML system can do, it can carefully select applicants from the first advantaged group while randomly selecting applicants from the second disadvantaged group just to make the numbers. Okay, this is actually is known as also in the literature as the self-fulfilling prophecy problem. Now, more intuitively, in case intersectionality or masking or both of them are likely to occur, it is not good for fairness purposes to aggregate individuals together. Okay, that is, we should treat them individually and apply or use one of the individual fairness notions, as this warning note tells us in the diagram. Okay, now let's continue with the second criterion, which is whether some standards or policies do exist. Okay, so in fact, in some real life setting, some policies are imposed to avoid discrimination. Okay, so for example, the guidelines of the US Equal Employment Opportunity Commission states that the difference of the applicability of acceptance between two subpopulations exceeding 20% is illegal. Okay. Another example might be an internal organizational policy imposing diversity among its employees. Okay. Now, as shown here, in case some standards are set, statistical parity is recommended to use. Now, in case some explaining variables exist, which are merely variables highly correlated with a sensitive attribute, but in a legitimate way. So here, let me give you an example. So assume we have a job hiring setting, and then the education level, for example, can be used as an explaining variable to explain the difference or the disparity between the male and female acceptance rates. Okay, as shown here in this table. Now, at this level of the path in the diagram, in case explaining variables are here, exist in the data set, so conditional statistical parity and no unresolved discrimination can be used, okay, or are suitable to use, depending on whether we are dealing with group fairness notions or individual fairness notions. Just here one note. So the choice of the explaining variables should be set or should be done carefully, and it needs generally the intervention of experts of the domain. Okay, and this is actually represents one of the difficulties of applying these notions in real life settings. Okay, now the last criterion I'm going to present is whether the fairness notion is more sensitive to false negatives or false positives. Okay. You know, in some real life settings, the system is like sometimes more sensitive to false positive rates than false negative rates, etc. So let's take here an example where the false positive rates is like more relevant, or the system is more sensitive to the false positive rates in a pretrial risk assessment. So it is typically known as it is more acceptable to let a guilty person go rather than incarcerate an innocent one. So at this level of the diagram, as you can see here, predictive equality is suitable to use, as it requires equal false positive rates among subpopulations. Okay, while here equal opportunity must not be used, as shown here in this diagram. So because basically this notion is totally insensitive to the false positive rates. So even if you have a huge number of false positives in your data, this notion will be totally insensitive to that. An example now of a system that is more relevant to false negatives is a loan granting applications, as we need to make sure that deserving people are not denied loans disproportionately from one group to another. Okay, so again here the diagram tells us that in that level of the path, equal opportunity is suitable, as it requires equal true positive rates among its groups, or among the different groups in the data. Now, let me show you one example of how we can use a path in the diagram to navigate it and to choose the most suitable fairness notion. So starting from the first note, in case intersectionality or masking are unlikely to occur and standards are not set, the ground truth is available, or the true outcome, we assume that it's reliable. The system is more relevant to precision rather than recall, or more sensitive, let me say, to recall rather than precision. The threshold is fixed, so equalized odds, equal opportunity, and predictive equality are suitable to use, depending on whether we are, or this fairness is more sensitive to false negatives, false positives, or both. Okay. So here, let me say that the goal of this presentation was to give you an idea about this applicability diagram. So I just showed or represented you some of the criteria, and the full details can be found in the paper. And for the ones who are more interested in the work, they can check our paper also in archive, which is a longer version of the work. Now, as in conclusion, I can say that with the increasingly large number of fairness notions in the existing actually fairness notions, selecting the most suitable fairness notion is not a trivial task. There are many contributing factors to that. So first, the boundaries between notions are increasingly fuzzy. Also, applying inappropriately a fairness notion might lead to unfairness, or might identify unfairness in an otherwise fair scenario, or the opposite. I mean, failing to detect unfairness while the system is unfair, is actually unfair. And the fairness criteria can be meaningless if variables are poorly defined or measured. Like, for example, choosing an unreliable outcome, or choosing a misleading explaining variables just to mask some discriminative intentions, or any other misleading variable. So the very reason of this work was to bridge the gap between some real-world case studies and the existing fairness notions in the literature. I think I'm done. Thank you for your attention. If you have any question,